do this. Okay, so basically last time we got to the point where, so sort of recap where we were at. And please, like, as I do this, if there's questions about this stuff, let me know. What we talked about last time, the really important thing we talked about last time was the idea of a partial derivative. And so from an abstract perspective, we thought about the partial derivative, I don't know, this is a nice symbol for it, f sub x, which we can think of as the partial with respect to x, let's say xi of f of x1 up to xn. We thought of that as being the derivative, just a regular old derivative of the one variable partial function. Or, so that's like sort of our symbols for what we were doing. In practice, what we did was we pretended all the variables were constant except one and took a derivative, right? So symbolically, we did this. In practice, what we did was, pretend all of the variables are constant except one, and take a regular derivative. So to remind you, we'll just do a real quick, say like I have a function that looks like f of x, y is equal to x squared y plus x. If you were going to compute its partial derivatives in the most straightforward way possible, take a derivative where you think, okay, y, this is telling you all of the y's are constant and all of the x's are variables. So you pretend y's are numbers, they act like numbers. So if you do that, the y gets left alone because it's a scalar. The derivative of 2x is, or of x squared is 2x. And so this turns into 2xy plus 1. X is the variable, y is the constant. If you took the y partial derivative, you pretend y is the variable and x is the scalar. So the derivative of y is 1, so this turns into x squared. But since x is a scalar, if we hold it constant, the derivative of x is 0 with respect to y. Okay. So that takes some practice to get back in your heads. Everyone in here has probably done this at some point at length. The next thing we did was we said if there was a tangent plane for a function, then it would have a very specific form. We said if you have a tangent plane for f of x and y is equal to z at AB, so if I have a tangent plane at a particular set of inputs in the input domain, say AB in the domain x, then it has the form, it's a tangent plane for this, has the form h of x and y is equal to f of a and b plus the x partial, the sort of slope in the x direction at that point times change in the x direction plus the slope in the y direction at that point plus change in the y direction. So we did a bunch of sort of geometric nonsense and took a cross product, but at the end of the day, this is what we coughed up, was the idea that we had tangent planes, right? So if a tangent plane exists for a function, that's its equation. And then finally, the last thing that we did right before the end of the class was I pointed out that the idea of having a tangent plane at every point in your domain is so important that we actually make that a definition. So we finished with the definition that f on some domain in R2 into R is differentiable at AB. I'm rewriting this in a more condensed form than I had on the board last time to make it more coherent, right? So we say that a function that takes a domain into two variables into one is a differentiable function at a point AB in its domain if h of xy is equal to f of AB plus fx AB x minus a plus fy AB y minus a is a good linear approximation. And you can think about that as being in quotation marks, but the idea is the tangent plane exists. Yep.
I remember calculating the number vectors negative fx, negative f(y)1. Why are they?
You add them back over to the other side, right? So when you do that computation and they're negative, when you compute the dot product, you end up with a z on one side minus a bunch of crap because of the minus fx and the minus fy. But when you add it back over to the other side, it shows back up as positive. Yep.
Is there a difference between the right side y minus b?
Oh, I'm supposed to write y minus b here for sure. Yeah, I mean, I want you to think like what's actually happening here is you're moving linearly away from the point A by sliding a little bit in the x direction and moving away from B by sliding a little bit in the y direction. Okay, so we have two goals for the day. The first is come up with some kind of notation that we can use to make this work if we have more than two variables, because this function theory is really useful if I could study functions of lots of variables with it. And particularly if you work in any sort of contemporary modeling, machine learning, physical systems where you have lots of inputs, you need to know more than fx and fy. And you can imagine this formula, if it's going to extend, is going to end up with lots and lots and lots of terms in it. I don't want to write 100,000 terms down with 100,000 partial derivatives. I want a shorthand way of writing it. Okay. And the second thing is, you guys have probably noticed, I keep sort of like not waving my hands, but I keep I'm prevaricating a little bit because I keep saying if the function is differentiable and if the function has a tangent plane. But I haven't told you when I know for sure that happens. Okay. So a big part of working in this kind of mathematics is deciding what the kind of object you need to do good calculus with is. So if I have this behavior, then the function is differentiable. But how do I know I can be guaranteed that this is going to work? Okay, so the answer is, so first let's deal with when are functions nice? Nice is a word that gets thrown around in math classes all the time, but nice for us is going to mean something about differentiability. So the question is, when are functions nice? So it turns out to be the case that one sufficient condition for a function to be nice, so this isn't going to be every nice function, it's not every differentiable function, but a condition I can put on functions that guarantees that it's differentiable. One answer is when the partial derivatives are continuous. So if you start taking partial derivatives of a function and they are also continuous functions, then the function they came from is a nice function. Secretly in your background, you might be thinking about conservative vector fields at this point. If you've seen this in any part of your life before, we'll get there. But partial, okay. That seems inconvenient. So partial derivatives being continuous is enough to say that a function is differentiable. So in practice, what that means is frequently we only work with functions that have continuous partial derivatives if we can help it. Or we define the domain of a function in such a way that we stay away from where the partial derivatives are bad. That's a theorem. F is a function that takes a domain not just in Rn, but in Rm, any sort of like vector input into R. If F takes a domain in Rn into R, has continuous partial derivatives, then F is differentiable. And when, again, by differentiable, from the standpoint of what we use vector calculus for, you should be thinking to be differentiable means I could work locally and represent it with a tangent plane or a line, right? The idea is the derivative gives us a good approximation for the function. That equation holds, right? This tangent plane is a good approximation for the function. And the second thing is that if we know differentiable, we know more about F. Here's another theorem. This comes up all the time in calculus. It's also called why integration is awesome. So if F is differentiable, it is continuous. So to be differentiable is to force continuity. If the derivative exists everywhere and is a good linear approximation for a function, the function can't be discontinuous. It must be a continuous function. Okay. Now, why spend the time talking about this? In sort of higher level sort of numerical approximation or science classes or physics where these type of vector calculus gets used, we want to know as much about the functions being nice as possible. And typically we have to make a restriction like consider only the space of differentiable functions so that all these calculus techniques actually work. So it's, in fact, the study of what functions are differentiable is an important part of these kind of mathematics. Okay, so those are called, loosely, these are called regularity theorems, right? It tells us when we're guaranteed to be differentiable, and if we're differentiable, we get this bonus property. Okay, so now I have the delightful task of reminding you guys about some ideas that you may remember from the past. First question is, I want to lift this up to lots of variables. I need a way of keeping track of all of them. What is the gradient? Isn't it? The first derivative, you said delta. What is, yep.
It's like all the differences from all x, y, z, and so on.
It's all the partials, right? Okay, so we're gonna have to build notation because we're gonna build what these differentiation theorems look like for big functions with lots of moving pieces, right? And we want a notation that looks like it. So this is where you're gonna start writing down homework questions, and your friends in calculus are gonna look at you like you're insane, right? So remember that the gradient of f as a function, say x contained in Rn into R, the gradient only makes sense for scalar value functions. The gradient of f as a function from Rn into R, again, what we're thinking of as f as a function of x1, x2 up to xm, is the vector of partial derivatives. So what do I mean? So we use this symbol. Some people write grad f. Why use 4 letters when you could use 1? Right? And what it's equal to is a vector that has fx1 in the first slot and fx2 in the second slot out to fxn in the last slot. It's the partial derivatives with respect to each variable arranged as a vector. Okay, so why introduce this notation? We're not doing anything with the gradient yet. We will in 3 chapters. For now, or 3 sections. For now, this is a notational convenience because I want you to, what I want to do is I want to say, okay, well, if I have this thing, h of x and y is equal to f of ab plus fx at ab, x minus a, plus fy ab, y minus b, if I'm willing to use vector notation, if I'm willing to use the dot product here and the gradient, I can write this in a much simpler way. This is equal to f of AB plus the gradient of f evaluated at the point AB dotted with a vector that looks like x minus a. I'll explain that. So what do I mean by these symbols, right? The idea is that we want to do this because this is going to allow us to talk about functions in n variables, not just 2. What is the gradient of f in this case? Well, the gradient of f at AB is just equal to a vector that has fx, depending on if you want to do a dot product or scalar or column, it doesn't really matter. You can think about it as a column vector, fxab. That where? Vector x minus vector a, yeah. So vector x is going to turn out to be the vector xy, and vector a is the vector ab. Okay. So if we allow the vector x to be the vector of all of the individual inputs, and the vector A to be the scalar coordinates of the point that I'm working around, then if I take this gradient and I dot it with this vector, what does a dot product do? First slot times first slot, which is this term, and second slot times second slot, which is this term. So this is an extremely compact way of writing down what it means to be the tangent plane of a function, right? So this notation has the benefit also of extending not just to functions of 2 variables, but to functions of n variables. Now it's hard to imagine in n variables what's happening because you get these things called hypersurfaces where you have n inputs and 1 output. So you're in Rn plus 1, imagining some surface floating around, and then there's a hyperplane that's tangent to it. But it doesn't matter if you can visualize it. What matters is even in n variables, this is still a good linear approximation for the thing you're working with. Okay. Okay, so the idea is, this is one of the notational use of the gradient is to collect up the idea, or to collect up a nice equation for tangent planes. Okay, is everyone clear on what's happening here? This is all we're doing is making a notation that makes this equation turn into this one. And if you compute this, you'll get that back out again. I mean, there's no way to get the f of AB in here, which is why it's still floating around outside the gradient. Now there's now there's an issue, which is I actually really want to extend this definition out to include functions that have vector outputs as well. This only works for scalar outputs, but the problem is dot products don't work anymore. So there's another way to write down the collection of all of the partial derivatives of the function. That is called the derivative. But it's the derivative as a matrix. Okay, so that was the gradient. Now we're going to write this function down another way. D is so df is the matrix with it's a 1 row by n column matrix. So it's a 1 by n matrix with row consisting of derivatives, of partial derivatives of f. Okay, well that sounds insane. What does that mean? So what I mean here is df is it's not a vector anymore. Here we're thinking about the gradient of f as being a vector fx, fy. It's a comma list that I think of as a vector I can dot with other vectors. Here, I'm going to think of this as a matrix with 1 row in it, and that row consists, each entry in the row is a partial derivative of f. We'll compute some examples of this in a second. I don't want to get totally lost in notation. We're going to write the notation down, and then we're going to compute with it. Okay, so this is a matrix. A matrix has a chance of being able to be extended because a matrix to be m by n and not just 1 by n. The reason we're going to do this is because we're setting this notation up to deal with vector valued functions. So how can I use df to describe what's going on with a tangent plane? Well, notice that for our function over here, just erase this for a second. We'll come back to the gradient representation. If, as before, I think of x minus a as being the vector x minus a, y minus b, for this problem, df at AB is equal to a matrix that has fx of AB and fy of AB as its entries. Well, this matrix times that vector is equal to this expression. It's regular matrix multiplication. df at AB times x minus a is equal to, well, how do you take a matrix and multiply by a vector? It's this entry times this one plus this entry times that one. It's just still a dot product. And so what you end up with is f, well, let me write it all the way out. X at AB, y at AB times x minus a I minus b, which is this entry times this one plus this entry times that one, which is fx ab times x minus a plus fy ab times y minus b. So another way of writing the equation of this tangent plane up here, notice all of this crud, all of that crud is this stuff, right? So another way of writing the tangent plane would be to write h of xy is equal to f of ab plus df at ab x minus a. So I can think of the derivative as being a matrix, or I can think about the derivative as being a vector. For scalar valued functions, these are the same. These notations are a way of collecting up the idea of a tangent plane with ideas that are very easy to work with symbolically. So let's actually compute some. Find df for f of x, y, and z is equal to, I don't know, how about x, y, z? That's a pretty good one. So I'm compute the derivative of f. Fx is equal to, hopefully this is okay with everybody. I heard somebody say yz. Fy is xz. Fz is xy. Is this the matrix or the vector? It's the matrix, right? Gradient is a vector, the derivative is a matrix. So df is a matrix that has yz, xc, and xy as its components in its first row. And if I wanted to compute the tangent plane, so the tangent plane at A, B, C, which I can call A. Okay, first off, why am I justified in saying this function is differentiable? Because the partials are continuous. It's possibly continuous with discontinuous partials. I have a horrible example of a function for that, right? The partials are continuous, which means the function is differentiable and also therefore continuous, right? So I'm even allowed to write this down because these are all continuous. So the tangent plane at the vector A, which is the point ABC, can be written as h of x, y, z is equal to ABC plus BC, AC, AB times x minus a. That's probably the simplest way of writing it. The value of the function at ABC, the derivative evaluated at x is equal to a, y equals to b, and z equals to c, times this vector x minus a. Oh, well. I have certainly invoked Siri more than once in my lecturing. It's not as bad as it used to be. So h of x, y, z is equal to a plus b plus c times bc, ac, ab, x minus a, y minus b. That's the nicest version of this. Why do I call this a linear approximation? I mean, it's the definition of a tangent for sure, but why? I mean, in what sense do I think of this as being linear? I guess is the, because if I'm going to say that this is a linear approximation, why am I saying that? So it's linear in the sense that, like, so yes, right, changes in x can be split because this is a matrix multiplication. So I want you guys to remember that what linear really means is a function is linear if you can do this. Linear means like you can pull a function apart like this, right? Another way I think about linearity is it's a flat sort of, linear means, I mean, it's precisely this, that like the function can be broken up into its action on individual pieces. And one of the things about matrix multiplication is linear. A times x plus y is equal to ax plus ay. That's something that you should have pulled out of your linear algebra class, prior to here, or 244, or whatever it is. And the linearity means that you're dealing with something that's flat and plane-like or line-like. And we call this a linear approximation because this is like the matrix A. It doesn't move. It's a scalar, right? And if you do little changes in x, y, and z, you can split it up into pieces in the same way that you can do this, right? Computers have a really easy time dealing with linear transformations like this, or linear functions. Things defined in terms of matrix multiplications are very easy for a computer to work with, as opposed to like high-level approximation. This curve itself, this might be really difficult for a computer to deal with, right? Because you have to do things like specify the number of points on the mesh that you're working with and whatever number of dimensions you've got. And every dimension you add, the worse it gets. Whereas over here, this is just a square matrix, or not just a square, matrix times a vector. Okay. So now we're tooled up to do the beefy theorem. Okay, so that was the definition of that. We did this tangent plane. I'm in the wrong set of notes. It's this set. Okay, so here's the full generality. And why we do this at all, right? The problem is everything we've done so far works for scalar valued functions. Gradients are awesome if the function is scalar valued. So if you have f that takes a domain in Rn into R, then you get these approximations that look like f of x is equal to f of a plus gradient of f at a times x minus a with the dot product, right? If you have a scalar valued function, you get this nice version of what it means to be a tangent plane. Gradient dotted with this vector that you're moving away from the original point with. If you have a vector valued function, that doesn't work because there's no such thing as gradient of a vector valued function. Doesn't make any sense. So if f takes a domain in Rn into Rm, we're going to need to do something different. So this is a vector valued function. You might think, well, why can't we just use scalar valued functions all the time? And the answer is, like, in a lot of cases with things you're studying are transformations of things in three-dimensional space to other things in three-dimensional space, right? Physical warps or rotations of physical objects, paths in space, might take in a position and spit out a vector. Okay? Force fields, for example, are vector valued. Okay? So you got a vector valued function. What is its derivative? How do I linearly approximate a vector valued function? And the answer is that we just extend the idea of not the gradient version of the derivative, but the matrix version of it. Okay? So when you think of a vector valued function, all I want you to think is you're taking in n variables. So here f vector. N variables come in and m functions come out. And we can think of whatever happens in the first slot as being f1, and whatever happens in the second slot is f2, all the way down to fm. It's not as bad as it looks. The example I want you to keep in mind is something like this. So you could have like f of x, y, z is equal to xy plus y, and then x squared y minus y squared. That's a vector valued function. It takes in 3 variables, it spits out 2 functions. In this case, f1 would be equal to xy plus y, and f2 would be equal to x squared y minus y squared. That just refers to whatever sits in the slot of the vector that pops out the other side. Okay. Okay, I'm going to define the derivative. The derivative of f is the matrix df, where on each row of the matrix, it's the partial derivatives of that slot of the function. So this first row is df dx1, df1 dx1, df1 dx2, df1 dx3, out to df1 dxn. First row of the matrix is all the partials of whatever's sitting in the first slot. Second row is all the partials of whatever's sitting in the second slot. df2 dx1 out to df2 dxn. This is much harder to do in notation than it is to do in practice. In the last row, dfm, because there's m slots in the function, dx1 out to dfm dxn. This bad boy is the derivative of f. So this is the matrix of partials. This is an enormously important object in computation because it's the way that you keep track of all of the different ways that this function can be changing. You can think here, what is this actually measuring, right? It's not just some abstract blob of partial derivatives. Each row of this is telling you how the function in that spot changes with response to each one of its input variables. This is saying in the x1 direction, this function wiggles in this way. In the x2 direction, the function in the first slot wiggles that way. So there's a lot of possible motions going on with the vector valued function. Each individual slot has n things it has to be able to respond to. All right, let's compute one. Let's compute one of that function. What is df? This function has 3 inputs. And oh, I didn't even put a z in here anymore, did I? How about I'll throw a z in? I'll put a z right there. There we go. Let's toss a z into it. So what is the derivative of f? Well, it's going to be fx, f1x, f2. Don't lose yourself here. df1 dx, df1 dy, df1 dz, df2 dx, df2 dy, df2 dz. Do you have to write all those down when you're doing this? No, I'm just doing it on the board because I'm introducing the idea, right? You can actually just compute this thing. So df dx1 is, okay, so first I'm going to compute all the partials of this function. With respect to x, we get y. With respect to y, we get x plus 1. With respect to z, we get minus 1. Now I'm going to compute the partials with respect to the second function. f2 with respect to x is 2xy. f2 with respect to y is x squared minus 2y. f2 with respect to z is 0. So this thing is the derivative of that function, or we call the derivative of that function. This is df. What is it used for? Well, it might not surprise you to learn that we just write down the same exact equation we had before. It's still true that if f is differentiable, then we can find this tangent, and it's kind of a, we're sort of in strange territory calling this a tangent plane at this point, but you can imagine it's a tangent plane. It's just a linear approximation is the best way to think about it. We can write a linear approximation for f by h of x is equal to df and a times x minus a. It's unmodified. Same theorem. Oh, I guess it would be helpful if I actually included the value of the function here. There we go. The vector to locate you at the start, and then the wiggly flat thing that we're approximating the function with. Yeah, this is the same. I mean, it's easy to get lost in this in the notation here, but remember, literally all we're doing with any of these things is y is equal to y naught plus m times x minus x naught. It's all the same idea. The y naught tells you where to start the approximation, the m tells you the slope, and the x naught tells you where the 0 point is, right? It's literally the same idea. This tells you the height or the vector to start your linear approximation with. This tells you what the 0 vector, what point you're approximating at. And this tells you the slope of this flat object that you're linear approximating with. It's literally the point slope formula, just beefed up to deal with vector valued functions and variables. Same exact idea. This is the beautiful thing about vector calculus, is that everything you already previously believed to be true is still true, as long as you're willing to write monstrosities like df down. Okay, does that make sense? At least in theory, it should make sense, right? The idea here is, and the power of this particular approach is that I don't have to modify anything about what I need to do. If I can work in partial derivatives and I'm willing to have a computer do a matrix multiplication for me, which is usually what you do, then you can linear approximate anything if the partial derivatives are continuous. All right, so I've blasted you with ideas here. But let me point, the last thing I'll say before, I've got some examples of some functions I want to show you guys on Math3D, which I've linked up. The last thing I want to say is, it seems kind of pretentious to call this a derivative. I mean, after all, when we think of derivatives, we think of all those rules that we learned in Calculus 1 for how to compute derivatives, right? And so one thing that you might have in the back of your head is, what does it even mean to be a derivative? What would be required? What gives me the right to say that something is a derivative? And the single most important property of derivatives, well, single two most important properties of derivatives are, it's linear. So df plus g is df plus dg. dkf is equal to k df. And the chain rule works. So the chain rule is what we'll do next time. But prior to that, I want to point out, this is we call this a derivative in part because this thing df, this is linear. What I mean is, if you imagine the d here as this matrix operation on vector valued functions, it is still the case that if f and g are differentiable, and so is f plus g, and df plus g is equal to df plus dg. It splits over sums. If it didn't do that, we wouldn't call it a derivative. It would be ridiculous. It would be stupid to do math if you say call something a derivative and that wasn't true. Likewise, if f is differentiable, k is just some number, say k is say an r, some scalar, then so is kf, and the derivative of kf is equal to k times the derivative of f. It acts like we expect it should. And again, the reason is because it's just a matrix multiplication running around in the background, right? Matrices do this. This is what a matrix does. It splits linearly. But this is the justification for all of it. If we couldn't say this, we would never call this a derivative. It wouldn't be useful unless it's split linearly like this. And I don't know, did I tell you guys this? We talked about the secret in here already, right? Which is that all of math is really just lines at the bottom. Like calculus is the secret that every function is secretly a line. I mean, it's not quite a line, but it's linear, right? That like some of the most useful mathematics that's ever been invented is linear mathematics. I don't tell Camp that, because then he'll tell you that the most useful math is nonlinear math and all this stuff is 200 years old, which is true, but it's still pretty useful, which is why you spend 4 years learning it in college. Okay. So what I want to do for the rest of the day, now that we've talked about this, is first, I'm going to answer any questions anybody has about any of this stuff if you have it. And then I want to show you some examples of functions that fail in different ways, like what a good function looks like with respect to the way its tangent line moves around, what bad functions look like with the way that their tangent lines move around, and because they're the sort of things that pop up in practice. And then I think we'll close it. I mean, a little passive reception probably didn't hurt after a bunch of abstraction. So if you don't mind me showing you some more examples, I'd be happy to do that. I will add that very rarely is this stuff when you guys actually deal with this kind of math in the practice, almost always it's at the level of this abstraction df. You'll be learning mathematics in vector notation, and it will be expressions like f of a plus df at a times x minus a. Rarely will you be computing these in practice by hand, right? But the methods that you're using will be built out of abstractions like this. In fact, the last time I looked at physics, it will all look like this. All right, so let me show you some functions. The other thing I'm trying to do is I can't minimize Zoom when I'm recording it. All right. Tangent trouble. Even the one I want. Okay. Here, if it loads. It's even the right one. I have another one of these open. Hold on. Is it this one? Oh yeah, here we go. Okay. So here's a function that has nice tangents. So here we got a regular old, like a beautiful paraboloid, right? That's about as smooth as a function gets as a paraboloid. And if you set up, all I've done to do this, now we actually know where these come from. This surface that I've drawn here, this is literally f of ab plus fx at a times x minus a plus fy ab times y minus b. And for some reason, it didn't want to do it with the parentheses, and so I had to expand it out. But that's all it is. It's a tangent plane, formally written out like this. So if you turn this dude on, and I've got this point on here so we can see where exactly that tangent plane is located. If we just let this thing travel around the parabola, what you should see is that the parabola is sort of smooth in the way that it changes, right? That there's no sudden jerks in the way that the tangent line slides around the function. It's very nice as it transitions from angle to angle. And if we let it travel in the other variable, we're going to see the same thing, right? That this is no matter how I make this thing travel, the tangent line varies smoothly as it travels through the parabola. The jerking that you're getting is when it leaves the domain and comes out the other side, right? But this function is smooth. This is a smooth function. As I slide the tangent plane around, the tangent varies continuously in both its direction, and at every point, it remains a good flat approximation for what the surface is doing at that point. Okay, this has continuous partials. It's a continuous function. It's differentiable. It's super nice. All right, now let's turn this off and do some worse functions. Here's a function that is, this function has partial derivatives everywhere. You can actually prove, we've looked at this function before, you can prove that the partial derivatives of this function exist at every point. But it's pretty clear that if you get into here and you try to draw tangent planes, it's going to be badly discontinuous, the tangent planes, right? Because you're going to get some tangent planes are going to come in looking like this. And from the other side, they end up looking like this. And there's this abrupt transition where they go from this angle to this one. They change abruptly in their orientation. So just because the partial derivatives exist everywhere doesn't mean the function is nice. The partial derivatives of this function have these god-awful singularities because of this x squared plus y squared in the denominator, right? And that makes them discontinuous. Then you've got oddities like, let's see, here's continuous partials everywhere, but not differentiable. Okay, this one is bad. Okay, so here's a function. This function looks pretty nice, right? I mean, it's continuous. You should believe it's continuous. Everything's connected. There's no asymptotes in here. But there is this weird looking kink here at the origin. I don't know if you can see the way that it's tried to color this, but it kind of twists just a little bit at the origin there. And so even though it's just locally down there, if you turn on the behavior of the tangent planes, so I'll turn on the tangent plane here. There's the point in the plane. there's a tangent plane. If I slide around with this tangent plane, it looks like it's changing pretty continuously. It's pretty obvious what's happening here is over here, it's tipped up like this. As you slide through this little trough, it flattens out and it comes up on the other side. That's continuous behavior, right? Everything's really nice here. Nice continuous change in the tangent planes. If, on the other hand, you slide through that weird kink at the origin, you end up with this weirdness. So as the point comes through, notice that the tangent plane looks like it's tipping over like this. As soon as you, that's steeper and steeper and steeper, you should believe that if I could approximate slight, like sharp enough, what happens here at just tiny, tiny intervals is that goes completely vertical. It goes like this and it tips vertical here, even though the function is continuous. As you pass through it, all of a sudden it actually changes orientation and like it just flips and now all of a sudden it's the other direction. So it comes in and it looks like it's tipping like this and then you pass through the origin, all of a sudden you're tipped the other direction and you flatten out. And that's not something we ever see in one variable. Here's a function that is continuous everywhere and the partial derivatives exist everywhere, but you get this bizarre differentiable behavior where at this twisted up point, you get this, you know, that just doesn't make any sense to say the slope looks like this and then 0.1 meter later, it looks like this without having passed through every value in between. It's like an asymptote in derivatives. I don't know how to make it more clear than that. This is weird. I'll turn this on so you can see like, oh, look, okay, so it's perfectly smooth. It's gonna come up from the bottom, everything very smoothly, and all of a sudden it goes apeshit, and then it smooths out again, right? This is the sort of reason why when you're studying these functions or using them in models, you have to be careful about what it is that you're modeling. If you say, oh, I've got some differential equation or some system, and this model's the system, and you include a point like this without checking it, you're potentially introducing behavior that you don't want in the system that is being governed by this, right? If you had some controller that was built out of a function like this, God help you, if you ever let 0 be an input, right? Because small changes in input correspond to wild changes in the behavior of the function. That's typically not something we want. Okay, now what is the last example I've got for you here? Continuous partials everywhere. Okay, now this one is an interesting example because this is, we proved a theorem that said, this is the last one I'll say, I would actually, if you guys ever have examples that you want to show me of things we talked about in class, this one is an example of a function that is differentiable. So this function is differentiable. It has a tangent plane at 0, it's flat. But the partial derivatives are discontinuous because on any cross section, what's happening here is this looks like sine of 1 over x. As you're coming in, what's happening is you've got this ripple happening, but the ripple is happening faster and faster. It's just getting smaller and smaller as it does it. So there's an infinite number of +1 and -1 tangent lines. So it's like just slamming back and forth from slope 1, slope -1, slope 1, slope -1 as it, you know, as it crushes into the origin. But because it's being controlled by a function that's going to 0 very quickly, it's also squishing it at the same time. And you may naively decide, oh, I'm going to study ripples on the surface of a pond. That looks like ripples, except I don't know about this. Like, if you came to me and said, I really want to do this function, I'd be suspicious. So just look at the behavior of the tangent planes as we cut through the origin here, and you can see it. If I could actually figure out which direction I'm supposed to roll this. So we'll let the point come in, and then what I want you guys to watch is the tangent plane goes bam, 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 and then smooth back out again. Come on, you can do it. And then we just see it, we should see it start wobbling faster and faster and faster and faster. Okay, so again, just because you're continuous and differentiable a point does not mean that you're well behaved there, right? There's more going on here than just the fact that derivative of tangent planes exist. All right, so you are well equipped to handle the homework attached to this. And next week, we'll talk about the rules of derivatives, including the chain rule. We'll talk about what it means to take a product of functions, to deal with compositions. And I encourage you, if you're looking at examples and you want to visualize them, use something like this to check out what's going on. That's how I do it.
Thank you.
Yep, take care.
Thank you.
Of the function.
See you guys.